these last couple pages are really just practice. There's tons of practice that we're going to do in the homework out of the textbook. But sometimes people will say, I just need more. I just want to make sure that I'm doing this right. It is a skill that needs to be mastered, writing these formulas. So that's really what these last couple sheets are for. So at any time here, you can pause the video, if you want to check your answers or jot them down. And then you'll have plenty of time to do that. I won't talk too much about these compounds, just some basics. As I'm looking at these 10, I see some with Roman numerals and some without. The Roman numerals are for transition metals, tin and lead. Transition metals, tin and lead. Metals that can have more than one charge. Somebody like sodium, calcium, potassium, they don't have multiple charges. They only come from a group on the periodic table that contains one charge. So you don't need a whole lot of Roman numerals, just when I'm dealing with transition metals, tin and lead. To find the charge on that transition metal, you kind of work backwards. So like with number 4, this titanium compound, I looked up chromate, CrO4, or maybe you have chromate memorized by now. That's impressive if you do. Chromate has a charge of -2 or 2-. In this formula, there are 2 groups of chromate, which gives me a total charge of -4. There's only one titanium, so to make this neutral, it must be titanium 4. Down toward the bottom, number 9, zinc has an optional Roman numeral. Technically, zinc is a transition metal, but 99% of the time, zinc is +2. So if you leave it out, that is fine. Or if you saw the name just written as zinc nitrite, and there's no Roman numeral in there, you can assume that it's +2. Otherwise, take a minute to look through these. You'll notice something like number 7 is 2 nonmetals. Number 3 is 2 nonmetals. That's the sign of a covalent compound, and that's when I can just name this thing with the prefixes. The spelling of pentoxide is kind of optional here. You can say pentaoxide or just pentoxide. Either would be fine. On number 7, we said you do not need mono on the first element, but you would need mono on the second. If I had 1 oxygen, I would have to say sulfur monoxide. In this case, I can leave the mono off the first, and I obviously need dioxide. So take a few minutes, look through these, see if you have any questions or concerns, but they really are just practice. When you're ready to move on to the second group, here they are, a mixture again of ionics, covalents. There's a hydrate in this group. We've got polyatomics. We've got transition metals, all this good stuff. If you can feel confident about writing these types of formulas, you're in really good shape. This is just a skill that is expected that you know how to do. Because for the most part, this was something from first year chem that we just need to refresh our memory on. If you're using that chart for the polyatomics at this point, that is totally fine and acceptable, because again, the more you use it, the more you'll get comfortable with those polyatomics and you'll kind of note their trends. Eventually, the polyatomics need to be in my memory. That's going to be a blast. So use that chart, look them up. The more you look them up, the more you stare at them, the more you just kind of get used to them. A lot of the same rules apply. There are more transition metals down in this half. A lot of polyatomics. Number 16, carbon tetrachloride. Carbon and chlorine are both nonmetals. That one's covalent. Another kind of goofy one that people will get wrong is 20. They want to put a Roman numeral by aluminum. But aluminum is not a transition metal, and it's always +3. It's always in the group that's +3. So aluminum will never have a Roman numeral, just aluminum cyanide. So again, feel free to pause this as you need. Jot down anything that you got wrong, or maybe you want to kind of fill in the right answers. These would be kind of good little self-quizzes. Here we are writing formulas from the name. And again, you don't have to show work, But it's not a bad thing to write the charge down. Or if you find that you're getting some of these wrong, check your charges. Did you use potassium +1? Did you get thiocyanate -1? Did you get the Roman numeral correct? Sometimes people mix up 4s and 6s, like down in number 9. The 1V is Roman numeral 4. So if you find that you're getting the formula wrong, that would be something to check. Did you get the charges right? Now, again, often I just think about the charges in my head, and I can figure out how to make it neutral. But if that's where you're going wrong, it may help to write the charges on paper. Number 1, silicon dioxide is a covalent compound, as well as number 7, sulfur hexafluoride. We've got another hydrate. That's kind of fun. Actually, number 5 is a covalent compound too. Notice in number 4, silver acetate. There's a good example of a silver compound where they're not giving you a Roman numeral. 99% of the time, silver is +1. So if they leave it out, you are totally fine using silver as +1. So as you need, go ahead and pause this so that you can jot down anything that may help you. And when you're ready, here's the last half of that set. Real similar. A lot of polyatomics, which is kind of fun. In number 13, we kind of mentioned like sulfate is normally SO4 -2. That hydrogen sulfate ion will be -1. Hydrogen is normally +1. So hydrogen with a -2 sulfate ion will give you a -1 overall. We also mentioned previously in something like number 14, tetraphosphorus decoxide. When you're dealing with non-metal covalent compounds, it's totally fine to have a ratio of like 4:10 or a ratio that may not be simplified. With ionic compounds, compounds containing metals, we should have the most simple ratio. So for example, like in number 12, vanadium +4 carbonate -2. I need 2 carbonate to make this neutral. Any ratio that varies on a 1 to 2 will give me a neutral compound, but I want to write that formula with the most simple ratio. So I need to leave it as 1 to 2 instead of saying like 2 to 4 or something like that. Note parentheses. I have to use parentheses when there's more than one of a polyatomic. Parentheses are optional if there's only one needed. So like in number 16, potassium dichromate. I need 2 potassium to balance the -2 from the dichromate. But parentheses would be optional since you only need 1 dichromate ion. Kind of the same thing with number 18. Dihydrogen phosphate. It's a giant polyatomic, H2PO4. Phosphate is normally -3. With 2 positive 1 hydrogens, that dihydrogen phosphate has a charge of -1. Parentheses would be 1,000,000% optional. The last section in here is just practice with acids, which is often what gives people the most trouble because it's not something that you had to worry about much in first year chem. You used a lot of hydrochloric, maybe some nitric acid, and that was probably about it. So remember we had said if you see hydro in the front, that's going to be an acid that does not contain oxygen. So like number 1, hydrocyanic acid is like hydrogen cyanide. Or number 6, hydrosulfuric acid is like hydrogen sulfide. Or hydroiodic acid in number 10 is like hydrogen iodide. When I see something like number 2 or number 3, there's no hydro in the front, so then it must mean that there's a polyatomic containing oxygen. If the ending is IC, it's the most common version, the ATE. So this guy here, ClO3 -1, I'll put that in there. That's the chlorate chlorate ion, the ATE turns to IC. So this becomes chloric acid. Acetic acid. Phosphoric acid is another good one. Phosphate is PO4 minus 3. Phosphoric acid must mean that the phosphate is bonded to hydrogen. And then I just balance it and make it neutral. The IC means that the ending on the polyatomic was ATE. If you see US acid, OUS acid, US acid, that must have come from the ITE version of the polyatomic. So this guy, SO3 minus 2, that was sulfite. One less, sulfate would have been sulfuric acid, the most common, most stable, SO4 minus 2. But when I see the ending turn to US acid, sulfurous acid, that's when I know that it was the ITE version of the polyatomic. One that's kind of annoying, these chlorates. So, we mentioned chlorate, ClO3, most stable, most common. The ATE turns to IC. Then there are a couple different options. You remember how you could go one less, and then you'd have the ClO2 minus 1, and that was chlorite. Okay, so this is what I expect. Chlorite, if he's bonded to hydrogen, turns to chlorous acid. You could also have this guy. Do you remember just ClO minus 1? That was hypochlorite. It's not on this group, but I'll just kind of mention it now. ClO had 2 less oxygen. So not only does it end in ITE, but we throw that hypo prefix in the front. This would just turn into hypochlorous acid. And the other option is down here. If I had 1 extra oxygen, we said it was ClO4 minus 1 per chlorate. So it just turns into perchloric acid. If the ending is ATE, in the acid form, we turn it to ic acid. So we would keep that perchloric acid. Kind of like if I did have this guy, HClO, I would turn that into hypochlorous acid. So we're mainly looking at the ending. If the ending of the polyatomic was ATE, the acid form will be IC. If it was as a polyatomic ITE, the acid will turn to US acid, OUS. So again, pause this as needed so you can check them over if you were using these as practice or a little practice quiz. Whoops, I went wrong way. There you go. And then this should be the end of them. This time we've got the formula and we're asked for the name. So there's that hypochlorous acid. Next to hydrochloric acid. If I don't see oxygen, then I put the hydro in front. Hydrochloric, hydrofluoric. Again, feel free to check these over as needed. Make note of any that you got wrong that you'd like to go through in more detail. But these last couple pages are 1,000,000% just practice.